Nimrod, Dr. Clive Wells, and Fred Bailey, and congrats on being happily married, Dr. Clive Wells. I did not know that. So, yeah, hopefully you all are doing well. I need more sleep, as always, and better lighting conditions in here for some reason. But Georg, welcome, and Peter, welcome. So, this is going to be a continuation, obviously, of the lecture that I gave yesterday. And today I'm going to be going into the specifics of how stellar systems are actually formed. Well, I say specifics, but really it's more of a, as with all things, more of a general overview. I'm not going to go into the nitty-gritty math, but I hope to give you a little bit more of a picture of how stars come into being, how planets come into being, that sort of thing, and what happens to that planetary system as it evolves over time, or what potentially could happen to that system. Because as I've mentioned before, we have, through the study of exoplanets, some oddballs, so we have actually quite a number of examples of stellar systems that look nothing like our own. And so, as I've said, any kind of model that we use, and the current one that we hang our hat on is called the NEAS model. And any sort of model needs to be not only explain what we see in our own solar system, but also explain what we see in other stellar systems. So, and yeah, today's episode is brought to you by Starbucks, because I seriously need coffee. I don't know why I'm going to mention this, but for the first time, I just used ChatGPT, and I have to say that maybe my foray into engaging with flat Earth is probably the sign that it might be going too far, because my first question that I asked ChatGPT was, is the Earth flat? And it gave me a surprisingly emphatic no, the Earth is in fact not flat. And then I asked it about gravity. But anyway, I did ask it what I intended to actually use ChatGPT for, which was to give me essentially a template for a mission statement for our observatory and planetarium and outreach and so forth. I don't know why I needed to feel that I needed to share that, but I just felt it, and so I did. All right, so let us get started. Let's add that to the screen. All right, as I said, yeah, actually, again, I can't seem to get off the subject. ChatGPT, I would like. This is just coming to me, basically. This is a solar nebula of an idea coming together. I think it would be interesting to get some educators in the community and get onto basically have a live stream about the implications of GPT from an academic standpoint, because it's becoming it's causing quite a stir among my colleagues, because apparently with the 5th iteration, it's starting to be able to actually answer graduate level questions accurately. And so my colleagues are often very consumed with the idea that cheating is bad, okay, and to prevent students from cheating. And so they see the advent of ChatGPT as a bad thing, and something that needs to be is a problem that needs to be addressed. And so I think it would be interesting to maybe get Clive on and see if I can get connect with Professor Phil Bell, Dr. or Tony PhD, get the PhDs together, and I can science that all the people that I know that are educators, and just have a chat about, well, GPT. I don't know if people would be interested in that sort of content, but it's like I said, it's a nebulous idea that's forming in my head. But speaking of nebula, let's talk about the origin of stellar systems. And I have to say that this is something that is near and dear to my heart. Part of my dissertation was half of my dissertation was talking about young stellar objects, or YSOs, and those are essentially, in layman's terms, those are protostars or forming stars. I was very interested in the reasons why these stars appear very, very chaotic, very, very variable, photometrically variable. And I was trying to at least start to come up with a framework for understanding what are the different types of variability mechanisms that may be present and what their observational signatures might be. And so, anyway, true, Clive, I've never had a computer on in any of my graduate exams, so yeah, I suppose that would be a non-issue. Although I don't know, maybe departments are moving in the direction of using more computers. I know computers are basically ubiquitous in the classroom for undergraduate, but anyway. So, as I've said before, the idea of, obviously, when we look at the space around us, we are initially dominated by the solar system, and so it naturally follows somebody would ask the question, where did it come from? How was it made? And so there were a number of theories that came up that have been come up over the ages as to how the solar system came into being. Ironically enough, as I've mentioned, as I've sort of intimated before, the first person to actually come up to basically guess right was Immanuel Kant, a real pissant. And in the 18th century, he came up with the basics of the nebular hypothesis. The idea here is you have a cloud of gas and dust that is separated or isolated in a certain way from other gravitational effects, and due to the fact that this cloud is a little bit more dense in the center than it is anywhere else, gravity takes over and begins to collapse this cloud down. Then you also have to account for the fact that the gas is going to rotate, and it's just as simply as that, is that you start off with a cloud of gas and dust that is slowly rotating, because pretty much everything in the universe rotates in one form or another, and just allow gravity to do its thing and collapse it down, and from that, boom, you get stars, planets, and all that. How do we do this? Well, let me back up a second. The idea of, and I have a feeling I've mentioned this before, but I will, at the risk of repeating myself, I will go over it again. The idea of young stellar objects, or this idea of a star forming from a cloud of gas, has a lot of observational backing to it, not just from indirect means such as photometry or photometric variability, spectroscopic measurements, but we now have direct images of it. Hubble actually gave us direct images of. Can I do this? Hey, I can do this. Show chat. Interesting. Okay, sorry. I just realized that I can actually expand my my stream to my full screen, so it's much more attractive to me. Anyway, I digress. So this idea, this nebular hypothesis, which again was first kind of came up in the 18th century and then has become more robust over time as mathematics gets thrown at it, as physics gets thrown at it. Excuse me. And so when we started seeing indirect observational evidence that this process is seen in other places in the universe. Because again, we want to be able to, in order to have confidence that that of where we came from, we need to really see evidence of it happening in other places in the universe. And we have direct observations of it. And then Hubble was the first telescope to actually give us direct observations of this. And we were able to, and the structures that we see matched the models that we were creating, which is as this cloud collapses, as I'll discuss, a disk forms, and also a jet of ionized gas that is moving relativistically, very, very fast, very, very powerful jet, moving away from the poles of the star. And we have used interferometric observations to actually image the disks of these stars in situations where they're not edge on like this, where we can see both the star clearly and also the disk itself. We also have some evidence from meteorites as to point us in the right direction as to how the planets actually came into being. And really, when I say evidence, what I mean is constraints. And so again, as I mentioned in the last lecture, any theory that we come up with has to explain what we see in the universe or in the solar system today. So it has to explain why we see different types of meteorites. We see meteorites that are, as I mentioned before, we have C-type meteorites, which clearly show signs of having been differentiated, where the heavier elements have moved to the center and the lighter elements on the end. And then you have S-type meteorites, which are not. Oh, flip that. C-type meteorites, which are not differentiated, and then S-type meteorites, which do show signs of a gradation of density. And we also see that meteorites, particularly again C-type meteorites, seem to be conglomerations of rocks or pebbles, which is going to give us a hint as to the process by which planets actually ultimately form. All right. I thought I had fixed that earlier today, but apologize for that. So, like I said, what exactly is going on? I'm going to basically skip over the YSO stage, but by saying that you start off with a roughly spherical cloud. Again, it has a slightly dense core. Actually, I can't see the. Okay. That's not where I wanted to go. Again, apologies. I'm messing with settings. I should just be happy with what I have. So you start off with this cloud, dust and gas, roughly spherical, slowly rotating a few kilometers per second. And again, the center is a little bit more dense than the rest of it. And as gravity is a function of both mass and distance, the inner part of the cloud collapses much faster than the outer part of the cloud. But the whole thing is collapsing down. What you ultimately get is, skipping a few intermediate steps, is that the cloud, or that the center of this cloud forms what we call a protostar. Essentially, it's a very large, on average, it's roughly around 3 times the radius of the sun, of the current sun. And it's pretty hot. It's not quite hot enough to go through nuclear fusion yet. It generates energy through that gravitational collapse that I was talking about. Basically, the conversion of the gravitational potential energy that it has as it falls, that gravitational potential energy is converted into kinetic energy, which is also the energy of heat. And that generates a tremendous amount of energy, heat, light, and so forth. And that protostar is roughly, we believe it to be roughly spherical. It's probably, given the rapid rotation, it's actually probably elongated at its radius, but you get the idea that you get this basic large concentration of mass at the center of the system that eventually will become the star, or for us the sun. Now, In addition to that, you also form what is known as it forms a disk. The rest of the cloud will form into a disk, and that disk is, depending on what kind of science you're doing, you name that disk differently. If you're interested in how the material falls into the star and builds up the star even larger, you call that an accretion disk. If you're interested in just the disk itself and the mechanics inside and the physics inside the disk, we call that a circumstellar disk. If you're interested in how planets form, then we call that a protoplanetary disk. Basically, it's all this. It's three names for the same structure. Now, to understand how this disk comes into being, you have to understand the idea of conservation of angular momentum. Conservation of angular momentum for me, is best illustrated by the figure skater. Figure skater, one of the more popular moves is they'll go into a spin with their arms out, and they'll spin fairly slowly, and then as they bring their arms in, they spin up dramatically, and they spin up quite significantly. Roughly speaking, the angular momentum is a function of how the mass is distributed and how the mass is distributed and the rotation rate. So as because angular momentum is conserved, that means if you change one aspect of it, then another aspect must also change in order to keep the value constant. So, for example, if you make the concentrate or the distribution of mass smaller, then the rotational speed has to go up, so it speeds up. And then consequently, if the the figure skater makes their arms go wider, then this figure skater will slow down, because again, if you make the distribution of mass larger, then the rotation rate actually drops. I feel like I'm missing the chat, so I'm going to actually go back to the ugly view. But the angular momentum, and so this conservation of angular momentum in application will produce this flattened disk because of something else called the centripetal or centrifugal force, however you want to think about that. But as hopefully you've all experienced, if you spin something, like if you put water on a ball and you spin it, then that water is going to fly out. And so as this cloud collapses, it's going to spin up because of conservation of angular momentum, but because of the fact that centrifugal force is a thing, it's going to cause that centrifugal force is going to essentially, it's going to battle against, I was going to say it's counteracted, but it's going to act against gravity. It's going to act to resist the collapse of the gas due to the gravitational interaction. But it's only going to do so perpendicular to the cloud. And so the stuff that is at the top and the bottom is going to collapse more than the stuff that is at the side, or basically in the along that kind of in the, at the midplane of the rotation. And so what happens is you cause it ultimately creates a disk. It speeds up faster and faster. The tops and bottoms squishes down, and it creates basically a disk like that, which is fairly rotating, or fairly rapidly rotating, as is the star. And so once you have that disk, that disk kind of stabilizes in terms of its thickness, and then from that you have the formation of planets. There are two ways you can hypothetically get, or there are two. Let me rephrase that. There are two mechanisms behind how you can get planets. The first one is it is not, one of them is not, in fact, relative density to equilibrium. The first one is actually hydrostatic instability. The idea here is it's an attractive mechanism in the sense that we see parallels out in other phenomena. So the idea of something forming a disk is actually rather common in the universe. We see disks pretty much everywhere. We see accretion disks around white dwarfs. We see accretion disks around black holes. Spiral galaxies form disks. So we see that all over the place. And so we like the idea of seeing this sort of consistency. And so gravitational instability, hydrostatic instability, is the idea of a planet forming very much like the star, but just in miniature. So I neglected to say that at the very, very beginning of all this, stars are formed in what we call giant molecular clouds or cloud complexes, where you have an immense cloud of dust and gas. We're talking thousands of parsecs in diameter. And this cloud is not homogeneous whatsoever. It has actually differences in density all over the place. And those dense pockets will cause those localized regions of gas to collapse in and upon themselves faster than the entire cloud would potentially collapse. And that's where those individual stars come from. So you take that and you make it you bring that analogy to the disk. So you have this disk of dust and gas, and that disk is analogous to the giant complex, the giant molecular cloud. And then within the disk, you also, again, have pockets that are not, again, this disk is not in any way homogeneous. The density is radically different all over the place. And so you're going to have localized regions of instability, or localized regions of enhanced density, enhanced gravity. And so it's going to start basically collapsing in upon itself in little pockets. And so from that, you can build up gas giants and possibly even brown dwarfs, but that's another subject entirely. Herman Bondi. I know that name. However, gravitational instability, for the most part, has been rejected because of the fact that the time scale involved is probably too long. It takes far too long for gravity, because gravity has a weak effect. It's the weakest of, as they've said, it's the weakest of the fundamental forces. Because gravity is so weak, it takes an exceedingly long time for any pocket of gas to collapse in and upon itself. But when we start talking about the lifespan of a protoplanetary disk, observations tell us that they only last for anywhere between 5 to 15 million years, based on the mass of the disk. The average is around 10 million years. Gravitational instability, in order to form a Jupiter-sized planet, for example, takes far longer than 10 million years in order to do that. It also doesn't explain where rocky planets come from, and so there are a number of other difficulties with hydrostatic equilibrium or hydrostatic instability as a explanation for planetary growth or planetary formation. But it's but the mechanism is still is bandied around and is somewhat discussed because of the fact that the process that I'm going to that we basically think is the more appropriate or the better explanation. That process really cannot explain the formation of planets that are very far out. So I mentioned last time with direct imaging, we're seeing Jovian sized planets that are, tens or even hundreds of AU away from their host star. The accretion process, there's no way that those there is not it. There's the density of the material is not high enough for accretion to actually take place. So it might be that both mechanisms exist and may operate simultaneously in certain systems. It probably didn't exist in our system, in the formation of the solar system, because again, we don't have evidence of Jovian worlds that are really, really far out there. But again, there are also problems with that with that again, because you still have the time problem. So how do planets actually come into effect? And we believe that this is, instead of a top-down, which we describe as the hydrostatic instability, where you have a large structure that breaks down into smaller structures, we're going from bottom up, which is basically, we call that the accretion process. So you have dust particles in the disk. The dust, or the disk itself by mass, is composed of about 10% of silicate material, of rocky material. And this rocky material, we're talking dust grains on the size of a micron, which is 1/1,000,000th of a meter. So very, very low, almost microscopic. Well, yeah, microscopically small. And so these dust grains are flying around, and they also happen to be they happen to be electrically charged. They're positive or negatively charged, probably positively charged, and or both. And so what happens is that as these dust particles are flying through the disk, as the disk rotates, they get close to each other, close enough for the electrostatic force to basically bind them together, and essentially static electricity starts building up dust bunnies. So the Earth wouldn't collapse from a rotating sphere in an accretion disk. More than likely, the problem is, as I'm about to get into, the problem is what with terrestrial planets, definitely, obviously, they are made up of rock. They're made up of silicate material. So this top-down process of a gas cloud collapsing doesn't adequately explain how you would get a predominantly rocky protoplanetary core. You would you would expect that from this process you would build up basically Jupiters. It's very difficult to explain why you would only have a small core. When I say small, I mean less than about 5 times the mass of the Earth. Why these cores would develop and then subsequently lose their outer envelopes. So yeah. So more than likely not. If it does happen, then that theory or that mechanism needs to be what's the word I'm looking for? Revised in some way or another. So you have these dust particles that get together, they clump together, and they form larger and larger particles until you get to about 100 meters in diameter or larger, and we refer to these as planetesimals. This growth occurs fairly quickly through the disk, and then you form hundreds, if not thousands. Actually, this is my swag or scientifically wild guess, is I believe the number is actually in the millions. You form millions of these planetesimals flying through the disk, all, like I said, of 100 meters or greater. At this point, you have enough mass in a concentrated small area that gravity can now be a thing, or gravity can now really have a stronger effect. Because as we know, gravity is dependent not only on the distance, but also on the mass. And so these planetesimals will attract each other and will slam into each other. And what happens, it depends on the violence of that collision of that meeting. And what I mean by violence is really how much energy is involved in that collision. If the energy is low for between the collision, what we're talking about is a large-ish planetesimal being hit by a smaller object, either a smaller object or a slower moving object, something that has a very low velocity. The kinetic energy of an object, how much energy it has in motion, is dependent on both its mass and its velocity squared. So in either case, a small mass or a small velocity, so much as that the energy involved is low, what will happen is that impact will occur, the site will become molten. The object, the planetesimal is more than likely molten or molten-ish at this point. The impact will cause it to be more further molten or hotter, and they'll basically weld together. They will be the planetesimal will get even larger. However, if the planetesimal, if the energy is sufficiently large, then what will happen is actually quite the opposite. You won't have growth. You'll have division. The impact will actually cause both of the objects to shatter into smaller pieces, which is why we only, out of those millions of potential planets, we only have 8. I really hate saying that, but I've got to keep to the party line. We only have 8 planets, and then you have Pluto, Ceres, and the rest. But in addition to that, then you have asteroids and comets, and this is where the term solar system debris comes in sort of a derisive sort of way, in that the asteroids and comets are quite literally these planetesimals that never quite made it into a planet. They never quite were able to smash together in a low enough or in a less violent enough way to get larger and larger, or as we'll talk about at the end of the lecture, some other planet may have come around and basically caused the planetesimals to scatter, and so they weren't able to actually meet up together and form larger planets. Jupiter is a bully. That's basically where I'm going with this, is that when we look at the planets, the one that basically punches down is Jupiter. So during this process of accretion, if we can go back to the disk for a moment, when we look at the disk, we notice when we look at the disk, we expect certain things to be true. We expect that there to be a temperature gradient. Well, first we expect that there's going to be a density gradient. The density of the disk is actually going to be higher in the inner portion of the disk, and then lower at the outer portions of the disk. It's not going to be homogeneous. Like, not only is it not homogeneous, but it's also got a density gradient as we go. But it also, and more importantly to our discussion, it has a temperature gradient. And we can see this by how the disk gets its energy. The first part, which I don't really have a slide for, is obviously the irradiation from the protostar. The protostar itself is generating energy. That energy flows outward. That will hit the disk, and that will heat it up. So in that way, hopefully it's obvious why you would have a temperature gradient, is because the inner part of the disk gets closer, so it gets more energy, or the fluxes or the energy per unit area is higher, so it gets more energy, and then as you move further out, you get less and less energy input. But in addition to that, you have again, this conservation of energy. You have this conversion of gravitational potential energy of these basically smaller kind of clumps of material within that collapsing cloud. And those will then slam, the ones that haven't already formed into the disk will then stream down, slam into the disk, and distribute that energy, distribute the energy of motion. So it first starts off as gravitational potential energy, that converts into the energy of kinetic energy, the energy of motion as it falls inward towards the disk. When it smacks into the disk, it will then dissipate that motion, that kinetic energy to its environment, which will essentially heat it up, and we get it go into the thermal energy. And so the inner disk is hot, and what that means, or the implication for that, is that certain materials can only exist in certain temperature regimes. So when you think of materials, astronomers we really like to simplify things. As I said, hydrogen, helium, and then metals. Now we have refractory materials and volatile materials. So refractory materials are materials that can survive anywhere in the disk. So the inner part of the disk has a temperature on average of about 1500 Kelvin. And then it gets colder as you move out. A refractory element, basically things like silicate, iron, nickel, think of heavy elements or rocks. That can survive anywhere in the disk, because the melting point of these materials is much higher than 1500. Well, is higher than the hundreds of Kelvin that you would find from 1500 Kelvin downward. Once you get to 1500 Kelvin, sand basically disintegrates or melts, essentially. So you have this material, you have this rocky material all the way through. Only until you get to about 5 AU, again, for a solar type system, once you get to about 5 AU or so, about roughly where Jupiter is now, the temperature is below freezing. It gets to freezing and below. And so from then, you can have water ice form outward. And then later, when you get even further and further out, you can have other elements start to form ices, more specifically methane ice and ammonia ice, which we see in Uranus and Neptune in higher concentrations. So yeah, like I said, refractory doesn't melt at high temperature. Volatile melts at moderate temperatures. And so I kind of skipped over something. I realized I needed to put a couple more slides in here. So when we have this, we have these planetesimals that are forming, and they are formed out of this refractory material. Basically these rocks, these metals, they form together. Then what you have is the accumulation of atmospheres, and so you have core accretion. That's what it is, and gas capture. That's the name of this mechanism. Once you start forming a core that is roughly around the size of the Earth, you can actually start accumulating something of a thick atmosphere. Now, the initial disk, the gases in that disk are very similar to the primordial composition of the universe. It's primarily composed of hydrogen and helium. So these atmospheres that are created around these planetesimal or the planetary cores are primarily composed of hydrogen and helium. But as you move further out in the disk, you start also having significant contributions of water ice, or then ammonia ice and methane ice, again, as you get further and further out. Well, you might be asking, Dr. Parks, we have an atmosphere, but we don't have a hydrogen helium atmosphere. Our atmosphere is actually composed mostly of nitrogen. Well, that's because we have lost our primary atmosphere. So we call this hydrogen helium atmosphere the primary atmosphere. So with the Jovian planets, we believe that there is a rocky core, roughly around 5 to 10 Earth masses, and then it was able to accumulate a large envelope of hydrogen and helium gas plus ices, depending on where it is, and it was able to hold on to that. There was a sufficient enough mass accumulated sufficiently quick enough that it is stable. That the gas cannot escape. The escapes or the velocity of the gases in the atmosphere are not sufficiently high enough to be able to escape the gravity of the planet. Not so for the terrestrials. Later on, when I get into planetary atmospheres, I'll get a little bit more into the specifics of this. But because the Earth does not have a dome, because it does not have containment, as it were, a physical container, we lost our primary atmosphere. Our primary atmospheres of hydrogen, helium, gas got basically escaped out into space. The reason for that is because the Earth has a certain scale any massive object has an escape velocity. The velocity needed to literally move away from that object and never return. Talked about this in my lecture on orbits. Half dozen lectures ago. If you have a sufficiently high enough speed, you can move away from the planet and never come back. Again, that is known as the escape velocity for the Earth. That is roughly around 11.7 kilometers per second. Hydrogen and helium are very low mass. They are the least massive of the gases, and so given a certain temperature, they're going to move faster than anything else, any of the other gases. And as it happens, more of their sufficient amount of the mass of a sufficiently large amount of this hydrogen and helium had velocities that were higher than the escape speed, they escape. So again, you might be asking, well, where did our atmosphere come from? Well, we can thank our atmosphere, the existence of our atmosphere, because of the fact of geology. The terrestrial planets at some point were geologically active, meaning that they were very, very hot, very, very essentially volatile. You have pockets of molten Earth, and then molten planets that cooled off, and as it cooled, it trapped these gases of material, because those gases, nitrogen and oxygen, do exist in the disk, just in much smaller quantities than hydrogen and helium. And so when these planets formed, they captured this nitrogen and oxygen, carbon dioxide, and these gases also got created through geologic processes as these planets formed, and they created pockets of high pressurized gas. And if the pressure builds up, then it can break free and get expelled, or in a process called outgassing, out into space. These elements are much heavier than hydrogen and helium, so even though they are they experienced very, very high temperatures where they were initially, the temperature was not sufficiently high enough to impart to them a velocity that enough energy to escape. So their masses really held us together. And in truth, we are a leaky ship. We are constantly losing gas to space. Our atmosphere is constantly depleting. But it also is constant for the Earth. It is also constantly being refreshed through ongoing volcanic and tectonic activity, or geologic activity. One of the reasons why Mars does not have a significant atmosphere at present is that it does not have ongoing geologic activity, and so there is no replacement to the gas which is lost leaking out. And the other thing that Mars has against it is that it's much smaller in mass than we are. Mars is roughly half the radius of the Earth. Controversial, no dome. So we have these secondary atmospheres. So right now, we have that Venus obviously has a very large or very well-developed, thick carbon dioxide, primarily carbon dioxide atmosphere, which again is really indicative of tectonic or volcanic activity. The Earth has a primarily nitrogen-rich atmosphere with a much lower concentration of CO2. I will get into why that is, the reason for that is. Again, because the disk has a temperature gradient, Venus was slightly warmer when it was formed than the Earth was, and so when the Earth cooled, it cooled sufficiently low enough that water could exist in a liquid state on its surface, and water is a tremendously good sink for carbon dioxide. It absorbs carbon dioxide very, very well. Venus, on the other hand, much too hot for liquid water to have ever formed on its surface, and so that carbon dioxide didn't have anywhere to go, and it just kind of stuck in the atmosphere of the planet. Mercury and Mars, they don't have their secondary atmospheres because, again, they are not massive. They are not massive enough to hold on to them, and I'll explain why that is later on. Well, Mercury, I'll explain it now. Mercury, we believe, wasn't massive enough because of a violent collision. We believe that at some point in its late history or late formation history, it was smashed into by a fairly significantly large planetesimal. And what that did was that it stripped off a great deal of its mantle material, which is why, and one of the reasons why we believe this is because the core of Mercury is overlarge. The core of Mercury, which is primarily composed of iron and nickel, is larger in ratio to its mantle than any of the other planets, which indicates that mantle material had been stripped at some point. Mars, as I'm about to get into, probably did not form larger because of Jupiter's influence. Now, I mentioned before that when we saw these exoplanets, we really had to we had to address the Nice model and put in we had to what's the word I'm looking for? We had to revise the Nice model. We had to look at the Nice model again and figure out how do we want to reject this model entirely, or do we want to revise it so that not only does it explain the solar system, but it also can explain these hot Jupiters that we see and these very eccentric orbits and so forth and so on. And in principle, the revision is referred to as planetary migration. And there are three general types of planetary migration. There's type 1, which is where you have think of it as a protoplanet is forming in the disk, and due to interactions with the disk, primarily drag, because the disk is still there, the protoplanet is plowing through that material. When it does so, it's going to be imparting some of its energy of motion into. It's going to be losing some of its energy, some of its momentum to the particles it slams into. And so as it loses angular momentum, it's going to fall inward. So this is primarily an inward migration mechanism. Type 2 planetary migration, often referred to as planet-planet scattering, is when you have planetesimals or possibly even fully formed planets gravitationally interacting with each other, and they will basically change orbits, change the orbit. And this is a chaotic migration mechanism in the sense that it is highly dependent on the initial conditions, the masses of the objects, how close they get to each other, what the trajectories of the objects are. And so this can cause planets to move inward. It can cause planets to move outward. It can also potentially cause planets to get ejected. And that is one of the theories of the solar system, in that we actually had a third ice giant. We had an ice giant that formed interior to Jupiter or interior to Neptune and Uranus, and Jupiter and Saturn kicked it out of the party, kicked it out of the solar system because of this planet-planet scattering. And then finally, you have Type 3 planetary migration, which is again gravitational in origin. Primarily, when you start getting these much localized, the local concentrations of mass, these basically gravity pockets or gravity wells, then you can start. Then objects start to experience heightened tidal forces, and through these tidal forces effects, so through these gravitational interactions, the orbits can actually get larger. And so this is primarily, again, it can, in certain circumstances, it can cause the planet to move inward, but it primarily causes planets to move outward. So we have now mechanisms to explain how you get these hot Jupiters through Type 1. We have Type 2 that can explain the very chaotic orbits of some planets that are highly eccentric or highly inclined, because again, it's a chaotic migration. It can send things outside the disk. It's certainly putting energy into the other body. If you add energy into an orbiting body, the orbiting body will become the orbit will become more elliptical. And it can also potentially, that can explain the chaos in exoplanets that we find. And then Type 3 could also be another mechanism for how we see these Jovian planets so far away from their disks, from their host stars. The NEAS model, when we look at the solar system specifically, the solar system didn't look like what it looks like now through its entirety, through its entire lifespan, or at least the outer solar system certainly didn't. So Jupiter, Saturn, Uranus, and Neptune did not, in fact, form where we see them now. And in fact, Jupiter, Neptune, and in some scenarios, it is believed that that Uranus and Neptune actually flipped. That Neptune formed interior to Uranus, and because of Type 3 migration, Uranus got ejected out to the outer part of it, or Neptune got ejected beyond Uranus and into the outer part of the solar system. And so here is this is the more accepted, or the more probable, I guess, model, which is called the Grand Track NEAS model. And you can see from the arrows that you have, that's essentially where the large orange ball was the primordial Jupiter. The yellow ball was the primordial Saturn. The first teal ball was the primordial Uranus, and then the last one was a primordial Neptune. So in this case, Neptune was always the furthest one out. But you can see from the arrows where they formed and then where they ended up. And actually, this is an oversimple, as many cartoons like this are. This is an oversimplification. Jupiter is expected to have moved inward not once but twice. And so from Type 1 migration, it is from interactions with a disk, it moved inward. It actually moved interior to what is now the asteroid belt. And because of that motion, because of that movement inward and movement outward, we believe that explains why Mars was stunted in its growth. And we also believe that is why the asteroid belt exists, is because, again, Jupiter's gravity prevented those planetesimals from coalescing into larger bodies. It basically scattered them away and caused the separations between them to be too large for them to slam into each other with any kind of speed. Now, you might be asking what caused Jupiter to stop. Like I said, it moved backwards and forwards at least twice. And the reason for that is because of Saturn. In this case, Saturn actually helped out in depending on how you want to look at it, in it caused Jupiter to settle down, get married, have kids, whatever. The gravitational influence of Saturn, along with the gravitational influence of the Sun, trapped Jupiter into its location. It basically locked it down into what we refer to as a resonance. So Jupiter and Saturn are in a 2-to-1 resonance. So for every 2 times that Jupiter goes around the Sun, Saturn goes around once. These sorts of gravitational resonances or locking, where you have integer or half integer pairings or half integer multiples of orbits, we see that quite a bit, particularly in the Galileans. We see that in some of Saturn's moons. So when you have relatively large masses and relatively small locations, it just naturally, these resonances naturally set up. Gravity just naturally places things in certain locations and keeps them there. So yeah. So here is another way of looking at it. So here you're basically looking down at the top down. This is in fact a simulation. The white dots are planetesimals that form that. So you can barely see it, but in this case, this actually is a simulation where Neptune actually formed interior. So the green line is Uranus, the blue line is, or purple line is Neptune, yellow is Saturn, and then green is Jupiter. And then the white dots are all planetesimals that haven't formed yet, or haven't formed into larger bodies yet. And then, so very soon after these planets formed, because of these planetary migration mechanisms that I've talked about, it evolves from left to right. So the middle one is an intermediate stage, and what we can see is that Neptune has already been not ejected, but pushed out to a much larger orbit than Uranus is. Uranus orbit for a while was very eccentric, or was much more eccentric than it is now. Jupiter and Saturn, again, were moving around. And then finally, things settle down, and you have Neptune in its further away orbit. Uranus is now further away from where it formed. Actually, Saturn and Jupiter are also further away than they formed, as the previous cartoon showed. And Saturn is actually more, has a larger elliptical orbit, or higher elliptical orbit, because of all of this kerfuffle, technical term, that happened during this period. And it was also during this period why you might be wondering where all those little white dots went. Again, they got ejected outward and they coalesced in either the Kuiper belt or also into a larger fraction of them formed into the Oort cloud. They got shot out into much larger orbits, much more chaotic orbits, higher eccentricities, higher inclinations, and created this cloud structure around the solar system. Now, you might be asking, so you had this really thick disk, and I said that the disks only last for about 10, 15 million years. Depending on the mass, or 5 to 15 million years, depending on the mass. Where did that disk go? Well, the disk can dissipate through basically 3 methods. Well, 2.5 methods. The first is obviously planet formation. Part of the disk gets trapped into forming planets, into these larger bodies, or asteroids, comets, and so on. Gases, on the other hand, can also get clombed onto the atmosphere, but both minute dust particles and gas can be destroyed due to what we call photodisintegration. So they get too close to the sun's energy is too hot, and it basically burns out these materials. The half part of it is that they then, along with the stuff that didn't get disintegrated, you have what is called solar wind. So light actually exerts a certain amount of pressure on anything. When a photon smacks into or interacts with a piece of matter, the photon has a certain amount of momentum associated with it. When it interacts with matter, it will impart that momentum onto the object it's interacting with. That will cause that can cause an outward pressure or an outward motion. And so the solar wind literally will blow these particles, the photons coming off of this protostar and ultimately the star will just blow out this disk, the stuff that the very small, very light stuff that didn't find its way, didn't find a home. So now I have a thought question for you. Suppose you observe a planet with an atmosphere composed mostly of hydrogen and helium. This planet likely formed A, close to the central star, B, far from the central star, or C, more information is needed. So I will let you answer that. You can put in A, B, or C in the chat. And I'll give you a couple minutes to do it. So again, if we see a planet that is composed of hydrogen and helium, the atmosphere is composed of hydrogen and helium, it most likely formed, may not be where it is presently, but where did it form? Okay, Judy says C. Just in the meantime, B. Georg says B. I'm thinking of finally. I've been meaning to address the JWST observations, which indicate that galaxies in the early universe are much larger than predicted, and I think as motivation, I'm actually going to set that up as a live stream where the first part of it, I will talk about what is the current idea of how galaxies formed in the early universe, how these observations, I will comment on whether or not the problems with the observations, what the observations show, and potentially the problems with the observations and why they may be premature, and the implication. But if they are correct, if these galaxies are in fact more massive than, or do have the masses that are initially predicted, why that seems to be in conflict with the Big Bang, and ultimately how, regardless, the Big Bang has not been debunked. All right, so Clyde, there is no D. So actually, the canonical answer is really the canonical answer is B. So you would expect that a planet with an atmosphere of hydrogen and helium would form beyond the ice line, and depending on where you see it, so it would form far from the central star. But I would say that Judy is actually correct, because again, one of the things that astronomy has taught me is to not just think spatially, but to think temporally. The information that we need in this is time. So we don't know when we are observing this planet. When in the history of its solar system are we observing this planet? If you remember, all of the planets started with a hydrogen-helium envelope. So if we're looking at a planet that is exceedingly young, then that star can actually form, or that planet could have formed anywhere in the disk. But if we're looking at an older star, and what I mean by older is really after a couple million years, then you're going to have then the answer is in fact B. So technically speaking, Judy is, in fact, the only one so far who's got this correct. More information is needed, and that information primarily is when or how old is this planet that we are observing. And with that, I will close out. I will end this lecture. And so thank you all. Thank you for those who are here in person. Hope you, as always, I hope you enjoyed it. I hope you found it educational. For those of you in the future, I also hope that you find this educational and informative. I really like doing these. So yeah. As always, like, share, and subscribe. And if you'd like to support my efforts here in outreach financially, all proceeds go to the observatory or the student club. Please hit me up on consider becoming a patron. You can name my firstborn or potentially name my firstborn if I ever have one, and among other goodies depending on your level, or just hit me up on PayPal. So thank you. I Bellywood, I did. What do you mean by I did? Well, I'll find out. So yeah, until next time, I hope you all well, clear skies, peace out.